In part C, we are told that when the capacitor discharges, there is an initial current of 14 amps in the chest of the patient. These are the values we have from before, and I'll keep them there because they might be useful. Then in the first part, we need to show that the resistance of the body tissue between the paddles is about 90 ohms. So we need to somehow relate resistance to one or more of the values that we have there. So an equation for resistance is R is equal to V over I, and you can see that we have both of those values known, which means we can put them in the equation and we will get 1200 over 14, and this will give 85.7 ohms, which is about 90 ohms as required. We then need to calculate the time it will take for 3/4 of the charge on the capacitor to discharge. So we start with a full capacitor and we give out 3/4, so we are left with just 1/4 of the charge. So if we think about the charge in a capacitor, which is given by Q is Q0 e to the minus T over RC, where R is the resistance in the circuit, C is the capacitance in the circuit. Q0 is the initial charge. Given that we are giving out 3/4 of the charge, so we are going to 1/4, we can say that Q, which is the charge at any time t, should be 1/4 of the initial charge. So we can put this into our equation and other values that we know. So we will have Q replaced with 1/4 Q0 being equal to Q0 e to the minus T over, well, we have a look at the resistance, that is 85.7, and we need to times it by the capacitance, which is back there 150 times 10 to the minus 6, and we can cancel the Q0, so you can see that the actual amount of the initial current is not really important. So we have 1/4 on this side and e to the power of minus t over this number on the other side. What we now need is to get rid of the e, which means we need to lin both sides. If we lin both sides of the equation, we will have ln 1/4 being equal to ln and e will cancel each other out, so we have t over this number, which is, if we multiply that out, 0.1286, and we can multiply both sides by this number now, also multiply by -1, so we have got minus 0.1286 ln a quarter being equal to the time. So we times this by ln 0.25, and the time will be 0.018 seconds. Going over to the next part of the question. The body resistance varies from person to person. If the body resistance was lower, the initial current would be greater. State how this lower body resistance affects the charge passed through the body from the defibrillator. So we are told that we have lower resistance, and this causes an initial current which is greater. How will this affect the charge? Well, if we have a higher current, given that we have a fixed amount of charge, because the capacitor has a certain charge store in it, and we have actually calculated it before, that will not change, because it's only about the charging of the capacitor, and it will store that fixed amount of charge, whatever the resistance of the body is. So the total charge to be discharged through the body will stay the same. But given that Q is IT, so the charge is the current times time, if you want to keep this Q fixed, if we increase I, then time must decrease. So we can say that this same charge flows in a shorter time.